Okay, so we are back after having done the computation, and sorry that first video was out of focus. I forgot to focus before we got started. So we applied. Why don't you talk me through how we applied our transformation to this graph?
So we have two areas that we need to change. We have going from 2. 2 goes to 4 and 5. So we took this set, and then so x became 2, y became 4, z became 5, and we got this set, and we made the new point w was 6.
Okay.
Then for this one, we did the same thing. We replaced x with 3, y and z stayed as 4 and 5, and then our new point w became 7 this time.
Okay. And so we tried to draw it out carefully in this graph. This directed graph became this directed graph. So actually, when I was preparing for this morning, this was much more complicated when I was just trying to draw it right from the rule, but actually writing out the connections significantly saved time. But you had an interesting question while we were doing this, which was what?
So I thought we could write these on a circle.
Okay.
So you leave one off the circle, and then you put the rest of their numbers on a circle.
Oh.
Maybe it would just be a better way to represent it. I mean, I'm just leaving 1 off because 1 just always goes to 2.
Okay, yeah. So now that we've done this, I think we can erase up here and draw these in. Actually, can you erase over there? And I'll give you. So why don't you draw? We haven't looked at this at all yet. So I don't know how this is going to look, but let's give it a shot.
So we start with 1 goes to 2, and then we want 3, 4, and 5. I guess this one doesn't look too different, just because. Yeah. So 2 doesn't go to 3. 2 goes to 5. 2 goes to 4. 3 goes to 4. Oop, that's not 3. But 4 does go to 5. 3 goes to 5. 3 goes to 4.
Okay.
So I think that's what we have.
All right. So that's just a different representation of this, but that's fine.
And then 1 goes to 2, and then we have 3, 4, 5, 6, 7.
Okay. So let's just be careful when we draw this out. So
2 is going to go to 5 and 6.
okay, good.
I guess so 5 here goes to 6. 5 also goes to 7.
3.
Nice. Okay.
I'm just going to go around here. 3.
3 goes to 5.
Yep.
And 3 goes to 7.
Let's see. So 4 goes to 7, 5, and 6. So 5, 6, and 7.
Okay.
I think that's everything.
All right, let's just double check that it matches. So 1 has a single arrow coming out of it. 2 has a single arrow coming in and 2 going out. We have that?
Yep.
6, yep.
Okay, let's just go in numerical order. 3 has 2 arrows going out.
5, 7, yep.
4 has 3 arrows going out.
5, 6, 7.
5 has 3 coming in, 1 going out.
Yep, that's what we see.
6 has 2 coming in.
3 coming in.
3 coming in.
Yeah.
6, and then 7 also has 3 coming in.
Yeah.
Okay, yeah. So actually, these two representations of the directed graphs are equivalent. Which do you think is a better picture of what's going on? Which do you like better?
I think maybe just keeping the points separate, and then maybe not having the lines cross over each other makes it a little clearer to see where everything is going.
What do you think?
I mean, I like this just because it kind of keeps the points ordered rather than just kind of a jumble. I mean, I guess the jumble is to prevent the crossing, but I mean, if this were a little bigger, I don't think we'd have an issue with the lines crossing.
Yeah, actually, it's a really interesting question when you're talking about these sorts of graphs, of whether they can be drawn without crossings or not. It's a very complicated question.
Mm-hmm.
Yeah.
Because what you're ultimately would be trying to figure out if these two were the same, right? And we checked it, but just from the picture, if they're the same, it's a pretty difficult question. So okay, so now we're going to go to Mathematica and look at some of the work as it evolves to be a little bit more complicated. I think you're really going to like this.
All right.